Okay, so we are doing the support vector machine. And at first, we want to do the support vector. So last time we did the support vector classifier. That is a special case of support vector machine. And it uses the linear classifier. So now that we do general support vector machines. So the textbook example is a little trivial example. So now that we just prepare a data set which is interesting for support vector machine. So support vector machine can deal with the nonlinear boundary. So we make the circle on the xy plane, and we want to classify the points inside the circle and the outside of the circle. So to do that, we use the unit circle, and we use the square of 3 by 3 square. So basically, the x coordinate negative 1.5 to the positive 1.5, and the y coordinate, I mean the x1 coordinate is negative 1.5 to 1.5, and x2 also negative 1.5 to 1.5. And the y, this is the label, is whether x1 square plus x2 square is less than 1 or not. So when the meaning is ambiguous, you can put the many parentheses, then the meaning is very clear. So at first, we calculate x1 square plus x2 square. Then we evaluate whether this value is either less than 1 or more than or equal to 1. So then we make a data frame. So just in case we remove x1, x2, y, because now we defined x1, x2, y as the global variables, but also the x1, x2, x2, and y are now also in these three. So that we just delete the global x1, x2, and y. Yeah. So if you can, plot x1, x2, maybe these three. Then what happened? X1, I think it's lowercase. So we have these points, but we wanna distinguish this by color. So the color is y, maybe these three y. So we have this group and this group. So if we have the circle, it's clear, but now we only have 200 observations. So it's not entirely clear what the boundary is. You can, of course, describe boundary, the b of x, the boundary for x-axis, 0 to 100 over 50. So this is just a cosine 0 to cosine 2 pi with 101 data points, and the sine also the pi 0 to 150. Then if you put, so originally we have the plot here, and and now we are doing the regression analysis. So we use first 100 observations as the training set and last 100 as test set. So the D3 x1 and the D3 x2, and the color is y, D3 y, And we overlay this with the boundary. So just we specify the range for X and range for Y. Otherwise, when you overlay the two plots, the X coordinate and the Y coordinate, so the X coordinate of one plot and the X coordinate of the other do not match. Okay, so now the plot, 100 observations. Then we overlay Bx, By, and we wanna make boundary as curve, so that we have to specify type is equal to L. And the X limit and Y limit, we have the same ones. And just for beautification purpose, that we don't overwrite the name of X label, Y label. Okay, then we have this. So now it's clear, but probably they cannot be estimated exactly because we only have 100 data points. If we have more data points, then probably we can estimate this circle more accurately. So think about the linear discriminant analysis. The support vector classifier, so linear boundary. Then basically it does not make sense. So for any line, basically that is meaningless. So even if the line that goes through this circle, then it does not make sense. And the line does not go through, then also does not make sense. Maybe possibly that we put line maybe tangent to this circle, then one side is all black dots and the other side are mixture of red and black, but it's really not clear what's the best method. So the linear kernel should not work well. Okay, so we use the first 100 observations. So this is data frame. So the row numbers are 1 to 100, and the kernel linear. Linear kernel doesn't have gamma, so cost. Yeah, depending on cost. Larger cost means the smaller classification error. Yeah. So this is within library. The function is within library E1071. So this way. So if we see the result, this does not look good. So this is classification. And yeah, so if you're doing classification, then we have to make sure that the SVM type is classification. And the support vector 83, that is basically not good because we have 100 data points and the support vectors are basically violating the rule, or at least on the boundary of the classification rule. So this is closer to 100, so that isn't really good. If this is small number, then it's really good. So, but anyway, so that is, yes. And if you want to see the classification rule on x1, x2 plane, you can plot SVM, D3, 1 to 100, okay, then this, okay. So basically it does not make sense. So we have two color, and this is basically, this should be within the circle. So the inside of the circle, and this should be outside of the circle. But actually the classification rule is that everything is, outside of the circle. So basically because the more than half of the observations are outside of the circle, so the best rule is okay, so always we decide the point is out of the circle, out of the unit circle. So you can see there's too many support vectors. The crosses are all support vectors, and the black are black points, black circles and crosses. So these are all the observations classified as false, so outside of the circle. So this is the classified as true. So, but actually no observation is classified as true. So it does not make any sense. So if you make a table for this, then yeah, so we can do the fitted value. So the predict SVM L original data set 1 to 100. Then if we make table of at first the predicted value and this is the true value, then this. So always predicted as false. So this does not make sense. So in the best scenario, this is 61, this is 39, and off diagonal terms are 0. But this is basically does not make any sense. So now that we try other kernel. So support vector machine is fun. So we use the polynomial kernel. So because we know that the boundary is this quadratic function. So if we use polynomial, then it should work well. And degree 2. Cost you can change, but okay, so for now we put 1000 because we know that this can perfectly separate the true boundary, so that we can separate the plane into the two, the truth, the true area. So the higher cost is probably good. So because we can make the error basically equal to 0. So yes, so then this is and SVM-P2. Then now that we see that we only have the 4 support vectors. So this is pretty good, pretty good. Yeah, so P polynomial with d is equal to 2. We have the several terms, the constant term, term of x and term of y, term of x square, y square, and xy. So 6-dimensional. So usually we have the 7 support vectors, but only have 4 support vectors here. So that means that even we don't really need the full 7-dimensional space. Okay, so now we predict, maybe we plot this. Then this is the estimated line. So this is polygon, so that it's not smooth, but you can see there what's the true boundary. And the true boundary is probably not the circle. So remember that we have the term of x square, y square, and xy implicitly. So this is ellipse, I believe. This is ellipse. And but still the classification is good, 100% correct. So all red points are within this region, so red region, the wine color region, and all the false, the points are outside, so the yellow region, so the cream, the region. So yeah, so for training set, this is perfect separation. So this is pretty good, and you can check this by, yeah, you can still predict. You can do the same thing by predicting function P2. Then also you can use this table function, predicted value P2. Then predicted. Yeah, I think this should be P2. P2. Then actually the perfect separation. And how about if we use the polynomials with degree 3? So now the d is equal to 2, but the d is equal to 3. Then we have some redundant terms, but still it includes all the second degree polynomials. So we hope it works also. Oh, I think the 2 is 2 and the 3. We have another object. SVM P3. But it does not look good. The support vectors, the number of support vectors is 86. It's really large. So probably it did not work well. So it's not clear what's happening behind the scene, but actually it does not work. So we can really see the reason. So this is the difficult part of the advanced method. So you can, yeah, maybe you can plot. SVM P3. And actually, this is the same as the linear classifier. So yeah, actually, it does not work at all. So we cannot detect this area. So yeah, maybe we can skip the table. And so the support vectors machine sometimes does not work depending on this D or cost function. So you can try the many values of the D and also cost, then you can potentially do well. I changed the cost function, but still it does not work well. So D is equal to 3 does not work. I don't exactly know the reason. So another thing is radial basis function. So basically we use some Gaussian, so the Gaussian distribution, Gaussian PDF to define the kernel. So this basically maps the original predictor space into infinite dimensional space. And also we cannot really imagine what's happening, but we try this. So this is radial basis, so SVMR. Then, okay, so it does not work as good as the polynomial with degree 2, but at least as better than the other cases. So if we do this. Yeah, so this shape is somewhat reasonable, at least for training data set, the 100% accurate. So if we make a table, so at first we calculate the predicted value. Then table, you can see perfect separation. But probably the SVM-P2 is slightly better because this has smaller support vectors. So that is probably more efficient to separate two groups. And also the ellipse, the boundary looks ellipse and the truth is circle. So probably it's a better approximation to the truth. So that we can we want to try the test error. We want to compare the test error. So to compare test error, maybe predict O. We can use still the predict function SVM-P2. Then we can just change the data set. Then table P2 and this. And usually the test set performance, test error is larger than training error. So maybe not perfect separation. And actually here that we have the two observations misclassified. So 98% correct, but still 2% that are incorrect. And how about the radial basis function, so SVMR? Yep. Then, okay, so 3. So this is pretty good, but the 97% correct and 3 observations incorrect. So probably that this polynomial with degree 2 is the best kernel for this one, because we know that the boundary is the quadratic curve. But in general, if we have this radial basis function, it works pretty good. And if you optimize some parameters, so this radial basis function have the one parameter gamma, so you can adjust that gamma, and also you can adjust the cost function. Then potentially it can do better. Yeah. So yeah, and one reason that the linear classifier and the polynomial with the degree 3 do not work at all is that we have the imbalanced data. So we have different number of observations in the group true and the group false. So you can see that this is the unit circle. So what's the area of the unit circle? Area of the unit circle is the pi times 1 times y. So 3.14. And the original data space is 3 by 3, so 3 square, so 9. So approximately only 35% of observations are within the circle. So so 35%. So for this kind of imbalanced data, the classifier does not work well. So you can imagine that the support vector machine has the large maximal margin principle, and the maximal margin means that we, they make the same margin for both sides, and that is good if the two groups have the same number of observations. But if it's imbalanced, probably that we have to make the area for larger groups slightly larger. Yeah, and yeah, so usually the imbalanced data, that this does not work well. So many of the machine learning methods does not work well if one group is much larger than the other. Yeah, so this is the how support vector machine works. So it's pretty automatic. So we don't have to do variable selection. Maybe you can do, but you don't really have to do. And you don't really have to manually put the quadratic term or interaction terms, but still we have to adjust the hyperparameter for regression, the radial basis function. So we have gamma, and also cost function, and the polynomial that we have the degree, d is equal to 2 here, and also the cost function. So we have to optimize parameters ideally by cross-validation. Questions? Okay, so next we discuss the support vector regression. So the textbook discussed the ROC curve. And the ROC curve may be useful to represent the result for classification problems. But the ROC curve, you can use the ROC library. Then it's pretty easy to create the ROC curve. So if you want to use the ROC curve, then at first you can Google the ROC library and ROC function. ROC function in the ROC library. Then it works pretty good. And now that we do the support vector regression, the support vector regression isn't as popular as support vector machine, maybe. But basically, we can use this for regression problem. So idea is a little different. So support vector regression, think about the tube around the true curve. And within the tube, that is within the certain distance from the curve, that we ignore the error size. But the outside of the tube, then we penalize those observations. So it's similar to support vector machines. Support vector machine only penalize observations which violates the rule. But if observations are classified correctly, then we don't penalize at all. Some people say this as support vector regression as SVR. We use the MAST library and the Boston dataset. Boston dataset is for the real estate price, and we have 14 variables, and the median value of houses, that is basically the response variable, and the other 13 are predictors. And all predictors have the reasonably high correlation with the median value of the house. And yeah, some are much higher than the others. This L stat and maybe the pupil teacher ratio or the number of rooms are high correlation with the median, the home value. And we want to apply the support vector machine, but we want to compare the linear model and support vector machine. And okay, and the training error is always the smaller for more complicated model. So support vector machine is more complicated model than a linear model. So if we calculate training error, support vector machine has much smaller error. So we have to compare this with test error or possibly cross-validated error. So here we use just classic, the training test approach, the validation approach. So sample 1 to 506. We have 506 observations in this data set, so that we take just half of them. This is the indices for training data set. Sample, I think this is sort sample. Oh, okay. So I think the parenthesis here. Okay. So training data set. So just the random 253 observations from the 1 to 506. And the test data set is remaining observations. So set difference of 1 to 506 and the training set. So the first 6 observation of had maybe 7. Number maybe 7, yeah. So then 7 observations. So actually 1 to 6 observations are first to 6 observations are all in the test set. 7th in training set, 8th in test set. So these are just mutually exclusive and exhaustive sets. So first linear model. So this is straightforward. So LM1, we name it, and the response is median house value, and the others as predictors, and the data set that we use the Boston data set and only training data set. And yeah, maybe there are too many observations, so maybe we use the stepwise procedure to select the best model. So these are the observations. The predictors remained. So actually the many predictors remained. So we have the, yeah, almost everything. So 5, 4, 5, 3, so 12 predictors. So originally we have 13 the candidates of predictors that we only dropped 1. That is which one? Actually, maybe included everything. crime zone. Yep. Maybe age. Age has been age isn't dropped. Room age, distance, the radius tax. Yeah, maybe. 1, 2, 3, 4, 5. Oh, this is the best model. So original model that we have maybe more variable. What is that? Yeah, the INDUS, maybe industrial, I think percentage of for industrial use of land space, maybe. So this is the selected model. So this is a baseline for this prediction model. So what is the performance, the the training error and the test error? So at first, training error. So if you calculate this root mean square error, that is the summation of fitted value of LM minus the Boston, median TST, and the take square. And yeah, summation and divided by number of observation, 253. Then no, training. So 4.565. So this is the training RMSE. So how about test RMSE? Test RMSE is the predict the LMB and dataset and Boston test dataset. Couldn't predict function. Yeah, and then test error. So test error is prediction LM, the Boston, the test set. Oh, median, probably this is fine. 9.38. It's a little strange that it may not work well for predict. It does not really work well. New data, maybe new data. Yeah, maybe we have to put the new data. Then what is the predict? Yeah, so this is the test RMSE. This is test RMSE. So 5.08. So the training error, the 4.65, and the test error, the 5.08. So test RMSE is 5.08. So this is the performance of the linear model. So we want to compare this with the support vector machine. So support vector machine, we can exactly use the same function. So SVM function. So support vector regression. And so median house value on this, so and this, yeah. So we just use the default value. So this is basically the kernel is equal to Gaussian radial basis function. And the gamma value that we can adjust it, but we can just use the default value. Maybe gamma is equal to 1. So the kernel has one parameter, hyperparameter gamma. And cost function default is 1. And just, okay, so we use that default value. Then support vector regression was done. Maybe we can see the results, support vector regression. We have 160 for support vectors, so probably classification isn't very good. Oh, sorry, the gamma is actually optimized by cross validation inside the inside the algorithm, but the cost function is not optimized, and the epsilon. Epsilon is allowed error size. I mean, basically the size of the tube. So maybe the width of the tube. So that is the 0.1. So we can also change this value to optimize the result. But for now, that we just use the default values. And for regression, this SVM type is reported as the epsilon regression. So epsilon is basically the band. So the size of the band within that band, the error will not be penalized. And okay, so now that we did the regression, because we can see that this was done as regression. Then we calculate the fitted value of support vector regression in the same way, just the fitted SVR. Then we can calculate the training RMSE for support vector machine, Boston medium, Then 3.35. So last time that we saw the 4.67, even though we optimized the set of predictors, that we did variable selection, still 4.67, but here the 3.35. So it's much smaller, I would say. And then how about the test error? So we have to use the prediction and the SVR and data, maybe new data, Boston test set. So maybe just see how these values are different. So this is the training set, and so this should be entirely different because we have entirely different data set. So test data, so entirely different. So now that we want to calculate this test error. Then 3.66. So certainly it gets worse than this one, but actually still it's pretty good. 3.66 is much better than this 5.08. So you can see the support vector machine can improve even without the tuning hyperparameters. Yeah, and maybe to evaluate this more accurately, then we have to do cross-validation. So this is just the one training and test data sets. So just the validation approach, the classic validation approach. Yeah. So in this way, the support vector regression also works. So if you are doing the regression problem in your final project, then you can certainly compare that with the support vector regression. Okay, questions? So we covered support vector machines and support vector regressions. SVM for classification, SVR for regression. Also, textbook has one chapter for one subsection for the support vector machine for multiple classes, the more than 2 classes. Okay, so that's it. And now that we go to chapter 10, and we only have 30 minutes. And yep. So just a moment. And the chapter 10 slides are available on the website. Also chapter 9, the R implementation is has also slides in Canvas. And yeah. Okay, so we are now, I'm opening the file for chapter 10. Share screen. Not sure. Okay, so now we do chapter 10. Yep. So chapter 10 is much different from earlier chapters. So we have discussed supervised learning from chapter 3 to 9. And chapter 10 is only the chapter for unsupervised learning. So what's the difference between supervised learning and unsupervised learning? So supervised learning, we have the X and Y, both are observed. And unsupervised learning, we only have X1 to XP. So from just the, not really predictors, but just from some variables that we want to summarize that variables, or that we want to identify, for example, how many groups in that, for that data set. So we don't have any Y here. Yeah, sometimes also, unsupervised learning has some objective. For example, they think about just the Chinese documents, maybe, millions of Chinese documents available, and without any, the supervisor, that we want to translate it into English. It's pretty hard, but it's not impossible. I don't know. I don't really know the Chinese language, but maybe the some letters that appear more often than others, or that kind of information can be useful to translate the one language to the other language. So that is also possible. So, but yeah, so usually unsupervised learning is more difficult because we don't have Y. And we study the two concepts. One is the dimension reduction. So basically, we summarize the information of X1 to XP into smaller number of variables. So we only cover principal component analysis. That was partially covered in chapter 5 or 6. And another topic is clustering. So categorize observations into several sets. So classification is also sometimes supervised learning. For example, if each observation have label, then that is supervised learning. But sometimes it does not have label. But you can see, for example, you can distinguish the 50 tigers and 50 squirrels. So that because their weight and height are totally different. So we don't necessarily need, the response information. So the answer, the label, to classify two groups. So if the two groups have much different, then we can still classify it into two. And we study k-mean clustering and hierarchical clustering. Hierarchical, I think one I is redundant. Is that right? Yep. And the principal component analysis that we have covered in the past. So basically, we do projection of all observations into lower dimensional space. So if we have originally X1 to XP, and if we choose smaller Q, for example, P is 100 and Q is 2, then Z1 to ZQ are defined by this way. So just linear combination of X1 to XP. So if P is equal to Q, just this is the transformation of X to Z. Yeah, then how to determine the Z? So Z1 is determined so that the largest variation of X1 to XP is included. So that means if we have, in a simple case, we have only 2 predictors, and how to define Z1. If we have these observations, okay, so these are on the 2-dimensional space, but if you think about this straight line, and we project all observations onto this projected line, basically it keeps, majority of, the majority of the information. So anyway, so these observations are almost close to this straight line. So if we projected these points, so this distance, maybe we have some center here. And if we think about the distance, just the coordinate here, then it includes most information. We have some small error, maybe this part and this part, small error, but if we project observation onto this line, then we can deduce most information of X1 and X2. So basically, we maximize the Z1. We maximize Z1. So basically, we need some standardization condition. So the Euclidean norm of this coefficient vector is equal to 1. So with this constraint, that we can determine this direction Z1. So to be exact, we have to use the eigenvectors to specify this. So Z1 is basically the coefficient phi is the largest eigenvector of the original matrix of X1 to XP. So X1 to XP are variables. So if we have n observations, then that is n by p. N by p matrix, right? So then, yeah. So if we consider that matrix as X, and if we think about the X transposed X, then that is the P by P matrix. And for that P by P matrix, that we can calculate the eigenvectors. Then the eigenvector is largest absolute eigenvalue that corresponds to the phi1. And after we determine Z1, that we consider the space, the perpendicular to Z1. So in this case, in this figure, actually only 1-dimensional space that remains. But if we have 3-dimensional space originally, then after we define Z1, the remaining space is 2-dimensional. Then we basically repeat the same procedure again. So in this way, we can we can define the Z1, Z2, Z3, and so on. Yeah. So we can approximate X1 to XP by Z1 and Z2. So we can regress X1 on Z1 and Z2. Then we can determine what's the characteristics of X1 to XP. So here we have the variables. X1 was urban population, x2 is the maybe the rate of the rape, and x3 is the rate of assault, and x4 the rate of murder. Then x1, the components, and this is the z1, this is z1, and this is z2. So z1 is highly related to these 4 variables. And z2, z2 is not really clear what that means, but anyway, so this is second principal component. So in terms of the tendency of crime, you can see, for example, where's Michigan? Michigan is, yeah, Michigan is not sure around here. I'm not sure.
Michigan is 2-0.
2-0. Oh, here, okay. So you can see that in terms of tendency, Michigan is closer to maybe New Mexico or Texas. It's further away from the Vermont or North Dakota, maybe. Yeah, so it's not clear what that means, but you can use the principal component to characterize the original observations.
Quick question. How would you say it is like in relation to Florida? Like it's more like to the right, but would it be like similar to it or?
Sorry, similar to?
Like Florida, which is on like around 0.3.
Yeah.
Or 3.0, sorry.
Yeah.
So it would be like sort of like in that realm with New Mexico? Or would like New Mexico be like, it would be closer, but like maybe like in relation to Texas?
Mm-hmm.
Okay. I just want to make sure I was understanding it. Thank you.
Yeah, so I don't know which is the closest, but in terms of the information included, yeah, so yeah. So we can just see the distance between those observations. So yeah. So I would say that originally we have 4 variables. Right, so each state have the 4 variables: urban population, maybe the number of rapes and the assault and the murder, maybe per capita. So originally we have 4 variables, so we cannot really see the 4-dimensional space on a paper. So we summarize the information in the best way, and then we can see that probably the Michigan is closer to these variables, these states. Yeah, and sometimes if we use principal component, it's easier to see the difference. Easier to differentiate the observation into groups. So these are actually supervised case. So each observation have label. So either green. So this is green, and this is orange, and this is, I think, the I don't know, the blue, or I don't know, but okay, so blue. And so it's not really clear. So this, yeah. So anyway, so if we see this as 3D graph, it's not really clear what's happening. But if we take the first component and the second component, Z1 and Z2, and the map all observations onto this, the 2-dimensional space, then you can clearly see what's the group, the here and the here. So these 3 groups are separated. So there is no guarantee that it's good for the separation, but since we keep as much information as possible, often in lower dimensional space, these groups are classified. in a good way. And if we consider the variance, for example, variance of Z1 and variance of Z2, since we maximized these variances, then Z1 is larger than variance of Z1 is larger than variance of Z2 and so on. So we can calculate what's the proportion of variance of Z1 over the summation of variance of Z. Then that is represented by here. So, okay, so this is, suppose this is 0.62, then this point is 0.62. So often we measure the efficiency. We see the efficiency of the principal component analysis by how many percentage of the variation is explained by the first few components. So in this case, the first component includes 62% of variance, and the second one maybe 0.22 or something. So first two components include 84% of observations, maybe. And if this is 8%, then already this is 92%, and so on. So these numbers are higher, then it's better. It's more efficient to use the principal component. This is cumulative case. So if we use the three components, Z1, Z2, Z3, then the most information is included in Z1 to Z3. I'm not exactly sure how many, what is the P, but yeah. Maybe this is 100, so probably only 4 variables. But if we use 2 variables, already the 84% of information is included. Yeah, questions so far? Okay, so now the last one is the clustering. So we studied the 2 methods. The one is k-mean clustering. K-means clustering, so is the given k that we identify which observation belongs to which group. Yeah, so basically the given k. So k-mean clustering means the k is given. The number of groups is given, pre-specified. So, for example, we have a group of animals, and we know that there are 3 groups in that entire group. So k should be at first pre-specified, and we will distinguish these 3 groups from without label. And the algorithm have 2 steps. And the first step is to calculate the center of each cluster. Then after that, to determine which cluster each observation belongs to. So yeah, so maybe it's good to see the example. So original data set is here. So this is unsupervised learning, so we don't have any label. And we are given k is equal to 3. So this consists of the 3 groups. Yeah, so it's not clear, but maybe at least the 1 group here probably. And the other 2, it's pretty vague. I'm not exactly sure. Maybe this is another group. Or, yeah, so it's really hard to imagine. Maybe around here, or maybe around here, or maybe this and this, or not sure. So at first, randomly assign the 3 groups. This is just the setting initial values. Three clusters. Then we calculate the mean of each cluster. So this one. So orange and the purple and the green. And this is the mean of randomly selected the orange circles, mean of orange dots. And also the mean of purple dots and the mean of green dots. Since these are random, these are almost the same. These are almost the same, but still slightly different. Then the second step, that we classify each observation. So for example, think about this observation. So this observation is closest to this orange center of the orange observations. So that we reclassify this, maybe this observation. So this observation was originally green, but since it's closer to this yellow, the center of the yellow, we just relabel this observation as orange. And the same things for the other observations. For example, this observation was originally green, but it's closer to this purple center. So we reclassify this as purple, and the same thing for green. Then it's almost done, right? So it's almost done. Then we again calculate the center of orange points. So we relabeled many observations. So the orange, the center of the orange observations comes much, upper left side. So around here, and the purple here and the green. And we repeat this again and again. So after that, we calculate the distance. For example, maybe around here, maybe closer to green center, so that we reclassify this as green center. And finally, that we can stop at some point, maybe after the no label changes, or maybe only a few label change. Then we can get the final result. So this is the k-mean clustering. Yeah. Any questions? So it may take more time than parametric model, such as linear discriminant analysis. But it does not require the label, so it's good to separate it. It's even with human's eye, it's really hard to separate it into 3 groups. But finally, yeah, so we have this. But I don't really know what's the truth. So it's not clear if this is appropriate or not. And obviously, this has, so these labels, so the colors are determined at random. So if the random assignment is different, that this group may be purple, and this is orange, and this is green, or maybe this is green, and this is yellow, and this is purple. So these colors don't have any meaning. So just depending on the initial state, it can interchange. Okay, so one disadvantage of k-means clustering is the k has to be pre-specified, but usually we don't know how many clusters are there in the original data set. And the hierarchical clustering that does not have that assumption. And we can classify as, yes, we can see it later, but we can consider all possibilities. So 2 clusters, 3 clusters. So we consider all possibilities for the number of clusters. Yeah. And hierarchical clustering, so the algorithm is here. So originally we have, okay, so this is 9 observations, and we start with the number of cluster equal to 9. Then after that, we choose the closest observation, and for all pairwise closest observation, and we just make one cluster here. Then next, we again, put the closest observation, so 1 and 6. And next, maybe 8 and 5, 7. So we have several ways to define this. Maybe we take the average of 5 and 7. Then we measure the distance between this and this. So there are several choices. But in this way, we can make the cluster larger, or we can make the number of clusters smaller. Then finally, we can get this. So this means that, yeah, this is, I think, the different example, but yeah. So the first, we group the 5 and the 7. So that means we have the 5 and 7 here. Then we have 8 here. And before that, we have 1, 6. So maybe 1, 6, and so on. And if we continue, that we can make this so-called the dendrogram. And after that, we can decide the number of clusters. So this is just, you know, this dendrogram itself is the result of classification. But if you assume that we have 3 groups, then we can just cut at this point. Then we can make one group, second group, and the third group. Yeah. So for our implementation, you can see the textbook. Yeah. So that's it for this semester. And on Wednesday, we have presentations. So we're gonna make presentation. I think that
I'm going Wednesday.
Yeah, Wednesday. Yeah, thank you.
Yeah.
Yeah, you can just check, and 13 minutes presentation. So just make sure that yeah, so 13 minutes presentation, and possibly plus 1 or 2 minutes questions from students or even me. And the outline is pretty pre-specified. So first one is introduction or background or something, and then you can discuss what kind of data you use. Then you can use the methodology. Then, you know, experimental results, the empirical result. And a summary. So this is the standard, the statistical presentation. And also many, the theoretical area have this structure. And of course, you can change the structure. For example, you have the 2 different analyses, then of course you cannot follow this exactly. So yeah, it really depends, but this is standard presentation. So unless special reasons, that you can follow this. So my advice is don't spend too much time on introduction. Yeah. So anyway, the empirical results, that is the main part probably. And if you have methods not covered in lecture, then you can discuss the methodology a little more. Yeah. If you have so many things to discuss in the methodology, just let me know. If you need more time, then I can give you some more time if you introduce the new models or something. Okay, so that's it for the semester. So the next time, yeah. So just to check which day that you have to make presentation, and also attend the both days unless special reasons. So, you know, just respect your classmates.